maybe one day we will get students from there. Okay, what I need to do? I need to.
So this is what I have. Now the problem is that I just tried it, yeah.
Is it a school project? Or just
Yes. I started my final project.
I need. Okay, 1 second. I need.
well,
Yes.
this will not
Rectifiers.
run very well because
I need to put rectifiers.
Then what's happening? The expected actually get something that was in there. Just look at
More rectifiers for the god of rectifiers. What about rectifiers? Wow. No. Rectifiers. What about rectifiers? Usually, people do ignore rectifiers. Oh, what about rectifiers? What can be complicated? But that's not so
this one is
simple.
okay, from the solar.
Why it's not
So we
simple?
don't have any backup system?
I didn't put a backup system.
Because
Just
today it's not like yesterday. Today we have all kind of electronics around us, and when we deal with all kind of electronics, not lighting, PWM drivers, home appliance, all its PWM power supplies and so on. And when we start from PWM power supplies, what we see? Rectifier. What a typical schematic of race unlock. So I need to switch. I need to appear. Okay. Oh, this one. It's a power supply from TV. It was unlocked flat TV. You know what happened? One guy threw it from the window. Flat TV. And this is power supply. What a typical schematic for modern appliance. AC input, fuse, maybe field, can be pair of capacitors and capacitor here. Next, rectifier, capacitor, primary coil of transformer, switch, ground, and of course PWM circuit, feedback voltage and control of the switch.
Where is this circle?
Feel it.
This is the filter.
Here, transformer, and here is the bridge, filter capacitors, switch, this transistor hides under cooling, and where is the filter? This is filter coil, nice double coil. I need more power supplies. Let's analyze this thing from the both sides. Now I have very simple very simple network. For the first approach, I made a very simple network. I have current sensor, switchable filter condenser, and simple load. The yellow signal is this one. It's an output voltage. And blue one, this one, ground is here. Maybe. Voltage at the load. And second one, please stay. And second one is the current. No filter. No. Sorry. What kind of spectrum? First channel. Here is the spectrum of the output voltage. It's classic, it's all time. 50, this one, 100, 200, 300, number 6. Spectrum of the output voltage. Here is output voltage, and it's contain harmonics with double M, where M is integer. So it will contain 100 and so on. This is classics from your electronics books. Yeah? It's classic. From your, oh no, what about your electronics book? Should be there, yellow line. And blue also. Simple sign. I have added 20 filters of 20 microfarads. What about electronics books now? What's going on and why? This is secondary voltage with small 20 microfarads filters. I can add 4. This one is 4. Filter capacitor charges and discharges. Who saw the yellow line? No one.
Seeing it where?
In your electron, it's kind of electronic course.
Sending it.
Come on. Rectifier with a filter.
Yeah, that's a filtered output.
Yeah, it's a filter output.
So if you make that capacitor bigger, can it?
I can make it bigger. Will be better.
Because the ripples are too much there.
Yeah. More and more, finally it will be a pure DC. Yeah. Now question with the blue line. Let's switch. What about blue line? Without filter. Oh. Ripple is high, yeah. But primary current is harmonic. 40 microfarads of filter. Ripple, oh, it's better. This way is better. This way, well, better. I can bring more capacitors. But what about this? What's going on? See what happens. Ideal case, no wall. I will show it big. It's a primary voltage. Capacitor charges to some voltage, yeah? Ideal case, no load at all. What will happen? We have diode between them. So until net voltage is less than capacitor charge, no current flows. At the moment what we got? Oh my, sinus omega. Capacitor voltage and ground here and ground here. We can analyze like this network. We will see short pulse charging capacitor. This pulse is a modern day reality. Where is my cursor? This pulse contains. Oh, wait 1 second. Here, it contains 50 Hz component, but it also quite 150, 250, 350, and so on. So this short pulse contains components 50 multiplied by double minus 1, where m starts from 1 to theoretically infinity, but not so far. Actually, this tail is quite short. So modern equipment with rectifier on its input consumes current in the form like this. More than, see this double spike. It's a third coming from network. This is was very small filter, only 20 microfarads. No filter, 20, 40, 80, well, I can add more. The better, second, this one is 200. 200. 200. Red is red. 200. Come on, you. Red capacitor. Don't think. It was a mistake to use this very small box. Will it work? Oh, it's 200. Very low ripple, but pulses are strong. Now, we have polyphase network. My good old three-phase law. Is powered. My good old, this will be phase T. 1 second, I'll assemble. Something. This will be okay. Red wire for phase C. This will go for phase D. I need more wire. One moment, I will get my three-phase network. I will. Okay, where the ground is now? This is ground. Oh. Here, I have a three-phase network. A, B, C, ground. This is signal 1, and I have point a current sensor in A phase, and this is signal 2. Can we check? This is A phase current, and this should be current of neutral. Let me check. I'll disconnect phase C. Oh, is 0. Very nice. What I need to do? Bring a modern load here. Load. Modern load, LED bulb, has a rectifier on its input. I need the second board. You know what it was? Someone's bed. This board, I took a wood from someone's bed. No. Oh. What do we see? Blue line is a current of phase A. I can disconnect it. As you can see, rectifier on the input, and we see this nice pulse for the character to rectifiers. Yellow line is a neutral current. I can, you know what I can do? One moment. I will say, at this moment, red line is a spectrum of phase current. Red line is a spectrum of this. 1 second, I will save it. Save waveform mask, save to first reference, show first reference. Oh, yeah. See, white line is a reference. I have saved a copy of the phase current spectrum. Now let's do one trick. I have switched my Fourier analyzer from the phase wire to the neutral. And what do we see? $150. We need to put it on a scale because we have the 50 hertz on the okay. This is 150. Oh. This way. Can you see the same thing what I'm saying? 50 hertz, 150, 250.
Why is 150 more than all of
Oh, yeah. Because that starts tricks. First, what determines angle between harmonics? We have polyphase network, three-phase network. What determines angle? These peaks are determined actually at moments when phase voltage is over the capacitor voltage. So angle between peaks will be approximately 120 degrees. Angle, voltage from actual phase angle at the first harmonic determines the moment when the peaks arrive. And next, what do we see? At the 50 hertz, we will see currents like this. This will be A, this will be B, and this will be C. The sum is 0. So 50 hertz on a white chart, 50 hertz present, but on a red chart in neutral, sum is 0. This is all what remain from the 50 hertz. Next, 150. It's a A, B, C. We again see the 0 sequence. Because 3 times by 120 means we remain at the same point. And this one is actually a triple third harmonic. Next one, 250. 250. A, C, B. That's what will be 250. Sum of them, it rotates clockwise, but sum of them will be 0. That's why we don't see, it's tiny. Next one, visible, will be nice. Where are you? Yeah. 250. Near 0, 350, 7th, 0 and 9th, yeah, 450, again triple. It's again. So, in neutral wire, in modern network, we will observe 3 times of the third and so harmonics. 3M harmonics. Fine. And what if I disconnect ground wire? Not a very good idea. See what happens with current. One second. I need to switch.
have this kind of history that I don't know where. Still difficult to me.
Phase current when I disconnect the ground wire. See, third harmonic disappears. And I see increase in phase harmonic and in fifth. With ground wire, without ground wire. And voltage increases. You see? Increase in voltage. It can cause damage to your client appliance. Okay, let's go forward.
Did you end up solving the cloud stuff? Come on, that's expensive. What we get it
I can remove this.
totally. No. Oh. If you calculate what would be your loss. So it's not necessary.
And take this nice object, three-phase transformer. Phase A, phase ground wire.
You have to buy for two things, and you buy them, and you have not one, only you have one to pick. One. So, most of the
Phase
things you like,
And where is my phase B? Here.
just try, but first you have to buy two things.
Three-phase transformer
Yeah.
connected.
Some
Start
people can
with ground, start without ground.
Yeah. So I thank you for sunshine, I thank you for rain, I thank you for pain,
Look what a nice rectifier I made. Here's my rectifier.
What is the power? Storage. Oh, okay. I have a lot of storage. For me, I think I'm done. I'm done with storage.
My schematics will be
You see this? This one
ground, A, B, C.
I have another one, 3 terabytes.
A, B, C, and. Okay, this can be grounded, and here I will have capacitor and some load. But at first I will have no load. Oh. Right to the left. More wires for the carpet wires. Green goes to green. And yellow goes here. And this okay, what I got? Something. What's on my yellow channel? Oh, on my yellow channel is 0. It's fully okay. And what about rating voltage? What about rating voltage? Oh. Well, it's not symmetric. I think we can live with this. What do I have here? My transformer with 3-phase rectifier loaded with 10 ohm resistance. What about course of power electronics? Yellow line is a rectifier voltage. Without any filter. And red line is spectrum. Something familiar? What about course of power electronics? 3-phase rectifier, full bridge. ideal world of rectifiers, full bridge, what will be free phase voltage? A, B, and somewhere here C phase. You see where it's going to? 1, 2, 3, 1, 2, 3. Here, double P omega. 6. 8 more. 6. 6 waves. Maybe I can add filter. $50,000 microfarads. See, ripple reduce. What's expected? And what about primary? Blue line is a current of phase A. Now, red line is a spectrum of output. I'm adding 50,000 microfarads. Ripple reduces. Very nice spectrum. Now, let's switch to the second channel. Without filter, we have spectrum of, who are you? 50 Hertz. And who are you? Oh, 250. 350 gap. 550, 11th harmonic. Why do we have this gap and this gap? Because I have an isolated neutral on the secondary side. Zero sequence or third, 9 and so on harmonic cannot flow. See? The center of the star is disconnected. On the primary side of transformer, if you have a really powerful rectifier with its transformer, I don't know, it's some metal board, there will be no third harmonic from rectifier. See this gas? Hop, hop. I'm adding filter. Here, how phase current looks like. You see this? Double waves. Three-phase rectifiers. If you have star-star connection, you will see not single wave like single-phase rectifiers, but you will get this double wave structure containing gap at third harmonic. This is number 5, this is number 7. And what about ground wire? 1 second, I will connect my scope. Where I will connect my scope? To the ground wire. Nothing in ground wire. Transformer magnetizing current. 1 millivolts. There will be no current in ground wire. I saw real guys, no, Rio Pro they failed this test.
Why?
Because you have a powerful, let's say, it can be also solar plant, but you have a powerful DC on the side. Actually, it's some kind of drive. Transformer, it's okay, fine. But since you have full bridge, not connected, center of the star not connected, third harmonic cannot flow. That's why you will never see neutral current. If there's 1 second, I can try to show it. I can try. It's a trick with so-called splitter supply. Idea. Ground and can be like this. In old time when mercury rectifiers were used, mercury rectifier 3 anodes, 1 cathode. So it will be something like this. Or schematics for splitted voltage. 1 second, I'll draw it. One of the way to get split voltage this is ground, A, B, C phase, ground, more capacitors. Again ground. This will produce schematics like plus ground 0. For example, outdoor systems use single phase, but for example, plus 110 minus 110 relative to ground and common 220. One moment, what I'm doing. I need, how can I get connection to the ground? This goes to ground. Here, connection to the ground. This what happens. I use connection to the ground. See phase, what happens with the phase current? Of course, ripple increase. And where is the ground? Here is the ground on the primary side. It's unbalanced. Now what I'm showing is an unbalanced schematic where load is against ground. It's old mercury rectifier and full bridge, but in a split voltage model. That's what you will get. And yes, in this case, you will get ground current, yellow line. This is case of normal full bridge. What can I do? More. Do something more. Something more is not a star connection, but delta. More complex thing is a delta connection of transformer. Here we sold star to star. Now it will be star to delta. I need 6 terminals. Not every one can connect star to delta. Let's see what happens. And what about voltage? Very little. Here is the phase current when I connect delta. See, that's the moment. Third harmonics do not exist in line voltage. Make So here, blue line is phase current. Again, we have 50 hertz, nothing at third harmonic, fifth, and seventh. And very small. So delta connection means less harmonic flow in network, but it's a bit more expensive. I can disconnect the filter, delta connection without a filter. Secondary voltage, yeah, it's ripple, but primary. Everything fine. Oh, it's filtered. It looks like this. And what about ground? What about ground current? 6 millivolts. Nothing in ground. No ground current at all. 6 millivolts. So if we speak about purity, delta connection is more preferred.
Sir, I have a question. For three-phase network, we don't need a neutral line, is it? For three-phase.
We can live without neutral if our load is symmetric. If
Yes.
there is a non-symmetry, you will see shift of center.
We assume
But
that-
for rectifiers, yeah, if we speak on rectifiers are symmetric, you don't need it.
So I assume that for symmetric network, it means the loads are balanced, right?
Yeah.
So what can cause the loads to be unbalanced? Because not all the times.
A lot of things. Number one, what kind of customers do we have?
Okay, there are those customers that just need three-phase.
Yeah, customer need, but customer can have three-phase load and have single-phase load.
But for small customers, like
For small-
homes, we need a neutral line because.
Yeah, for small customers, you always should predict the case when one switch, for example, on water heater, and on the other side is only small TV.
So the loads are unbalanced there.
Yeah, this will shift the neutral point towards the lower resistance, and you will pay, theoretically you will pay for a new TV. I have a demo video, it's called Do Not Disconnect Neutral on my channel. For the larger group of customers, the less predicted neutral shift. But there is one more moment. Imagine fault. One of the customers made ground fault, and one of the fuses burn. If you don't have neutral, bad things can happen because voltage will rebalance in reverse ratio to resistance. Bad things happen. No, for distribution, it's better to have neutral. But for let's say 0-4. But for I don't know 3, 6, and so on, neutral is not needed. Transformer will. Delta or better transformer, and no. See, here, for example, in our case, all connection 10 or 20 kilovolts to the customer to 0-4 are three-phase. For example, in his case, where on each pole single-phase transformer, one disconnect and customer receive absolutely not he's paying for. Customer wants 230 and may receive line voltage. 400, customer will not be happy. Okay, what more? It's very nice three-phase. Also do exist in our 12-phase rectifiers. transformer with two secondary winding connected via current limiter. They produce so nice voltage. Fine. Return my star connection. I needed a switch. Nice rectifier. Green. Are you green? BTV. Effect. 1 second. I will. Little trick, effect of one phase disconnect. I'm disconnecting phase C. See what happens with output voltage. All phase connected. C phase disconnected. A phase disconnected on a secondary side. C phase disconnect on the secondary side. It was without filter. Now I will put filter back. With the filter, C phase disconnect on the primary side. And C phase disconnect on the secondary side. See, if I disconnect one phase, three-phase rectifier becomes simple bridge. And one moment I will reconnect to ground wire. C phase disconnected on the secondary side. Small current. C phase disconnected on the primary side. C phase connected, C phase disconnected on a primary side. Yellow line ground wire, blue line A phase. This may help you sometimes make a smart phase. And C phase disconnect on a secondary side. No change in ground wire. Hot. Time? Yeah. Okay. Now I can